we take up the second talk on determinants. In the first one, we pointed out how the determinants arise in the context of solving linear equations. And then of course we said something about the properties when we were confining ourselves to the 2 by 2 determinants, because to get a feel of the problem. Later we will generalize it. Before we generalize it, it is better to look at in depth what happens on this 2 by 2 case, because that will give a insight into the problem. As I said in the beginning, that determinants are not something arbitrarily defined. In fact, I don't have to stress any more about the utility of determinants in the context of solving equations. And it's a very handy notation, and it's also a certain map on certain spaces with remarkably beautiful properties. And this we have explored in the case of 2 by 2 determinants. Now our problem is not merely to generalize this to the context of n by n determinants, but explore what is the structure that works behind this beautiful object. And one should suspect that if you come across a particular example in mathematics where you see unusually exciting properties which can be observed, then one should suspect naturally that there is a deep structure which gives rise to these properties, and that's very important. And we are in this context, we are trying to explore what kind of structure essentially gives the so-called determinants. Our determinants are, if you take a n by n matrix, the determinant is crafted in a very peculiar way, which is not immediately obvious. Secondly, it has some very fascinating properties, and it has tremendous applications. All these specialities are there for determinants, and therefore one might ask a question, why not define it in some other way? But this comes out naturally in the context of solving linear equations. That's what we observe, and we observed that there are some very nice properties, and therefore we should suspect that it has to be somewhat intrinsic to the matrices. Okay, it's a sort of number that you associate with a square matrix or a scalar that you associate with a square matrix, not arbitrarily, but structurally supported by something. That is what we are trying to explore. in a way, I would say that this is a sort of intrinsic scalar that you associate with a square matrix. Okay, let us explore this in the context of 2 by 2 determinants. So instead of working on general field F, I mean whatever I do on R2 can be pushed across to the general field. I mean there is nothing, no problem about it. Okay. So, so we work on what are called bilinear forms. Now, this is something where R2 can be replaced by F2. There is no problem. Okay, but let me not do that at this stage because our objective is to get the feeling for this. So we have seen what exactly is a bilinear form. If we start with a 2 by 2 matrix, so let then we have seen that what you call determinant of A is defined as A11, A22 minus A12, A21. In fact, we have seen that this is an association with 2 by 2 matrices with a scalar. Okay. So let me just do something. So let me write A1 as the vector A11, A12, two components of that. A2 A21, A2 I write as A12. That means these columns are identified as vectors in R2. Then A1, now we look at what is called R2 direct sum. R. Now you see that this is a vector space with possibly with a basis E1 0 E1 E2. Now I am not going into the structure of this, so that is easily available, which is not relevant to us. Now let us define a map from R2 direct sum R2 to R in the following way. Let map from denoted by B xy. Now this belongs to R such that B is linear in the first argument with the second argument fixed and is linear in the second argument with the first argument held fixed. So actually the ordered pair x coming from R2 and y coming from R2 is mapped to a real number, and this map has the following property, that it is linear in the first argument when you keep the second argument fixed. It is linear in the second argument when the first argument held fixed. That is, let us write it explicitly. These properties are the B of y and B of x c1 y1 plus c2 y2 equal to c1 b x y1 c2 b for every x1, x2, y1 belonging to R and C1, C2 belonging to R. And this is x1, x2, y1, y2 belonging to R2 and C1, C2 belonging to R. Then we say B is bilinear that's a definition that you have. So you can easily generalize it. Okay. We will look at the generalization when we come to that. But for the time being, we use this and we can talk about multilinear forms or a bilinear form. It is essentially a what you call functional, which is a bilinear functional. But instead of calling it bilinear functional, let us call it bilinear form. Okay, so that's the definition of this. Now observe that determinant of A, okay, or I can put it this way, determinant of A, which can be rewritten as determinant of A1, A2. That means these two columns, okay, is a bilinear form In fact, you see that if you just take A1 dot A2, okay, for example, you see if you take B X Y X dot Y, with the usual inner product. Now you see that this is a bilinear form. So it is because determinant of A is a bilinear form that we are interested in this. Therefore, now you see we go ahead with our usual practice in mathematics, namely we are interested in finding out what determinant of A is or how it arises naturally. But for that, having observed that it is a bilinear form, we would like to look at the class of all bilinear forms on R2, okay, and then look at its structure, and from that we will try to work out this. So we are interested in the class of all bilinear forms. So class. Let BR2 denote this class. First of all, you can show that this is a vector space. So our first claim is that BR2 is a vector space. First thing that you observe is this, that is BR2 following addition and scalar multiplication is a vector space. over R. It's a vector space over R. Now we will define the addition. If R2, then define B1 plus and CB1, CB of it's clear what it is. You see that B1 plus B2 is defined as, that means its image of xy is taken as B1 xy plus B2 xy, and image of CB that is C times B is defined in this way. What does it do? It maps again R2, direct sum R2 to R. Is it bilinear? That's what you see. B1 and B2 are bilinear. Therefore, it is quite easy to verify that B1 plus B2 is bilinear. So also CB is bilinear. Okay. Therefore, both B1 plus B2 and CB are bilinear forms, and I am just skipping the verification of this because it doesn't take time, or I can just show how it comes. So you see that B1 plus B2 this by definition is plus B2 that is our definition, and you see that B1 and B2 are bilinear. Therefore, you have got this is equal to alpha 1 times B of B1 of x1y plus alpha 2 of B1 of plus alpha 1 of B2 of plus alpha 2 of x2y. Now just write this as alpha 1 therefore, this is equal to alpha 1 of B1 of alpha 2 of alpha 1 of b1 plus b2 . So that is actually b1 plus b2 alpha 1 x1 plus alpha 2 x2 y equal to alpha 1 times b1 plus b2 x1 y plus alpha 2 times b1 b2 of x2 y. Okay. Therefore, it is linear in the first argument when y is held fixed. Similarly, you can prove the other things. Now, similarly, the entire set of linearity is proved. I have just proved this. Similarly, other steps are therefore, you see that if b1 and b2, b1 is a bilinear form on R2, b1 plus when b2 is also a bilinear form on R2, then b1 plus b2, if it is defined in this way, is a bilinear form. Similarly, one can prove that for a scalar c, cb defined in this way is also a bilinear form. Therefore, it forms a vector space. Okay. Now, naturally, one of the questions that you ask is the following. What is the dimension of the natural question? I mean, this is very simple linear algebra questions that you keep asking one after another. Okay, what is the dimension of BR2 over R? This is the natural question that you ask, which amounts to possibly working out a basis for this space. Okay. Now, before that, we have to verify that, okay. So the question is, before that we B is completely determined by its evaluation on and where E1 equal to So standard basis vectors for R2. This is easily seen because let us work on this. Bxy is equal to B of alpha 1 E1, or I will put it this way, x1 E1 plus x2 E2 y1 E1 E2, where x1 x2 Fine, this is not the earlier notation that we have used. Okay. Now these are elements of R. Now that's equal to use the bilinearity. Use the bilinearity, then this is x1 y1 E2. That's equal to x1 y1 x1 y2 x2 y1 E2. This is it. Therefore, once you fix B E1 E1, B E1 E2, B E2 E1, B E2 E2, then B is completely fixed using the bilinearity. Okay. That is clear. Okay. On the other hand, suppose you fix B E1 E1, B E1 E2, B E2 E1 and B E2 E2, then you can define Bxy using this working backwards, okay, and that will define a bilinear form on R2. Okay. Therefore, it is enough to know the values of B on E1 E1, E1 E2, E2 E1 and E2 E2. Then B is completely determined. So that we keep in mind. Of course, this is, you see that E1 E1, E1 E2, E2 E1, E2 E2 is not linearly independent on R2 direct sum R2. That is something that you have keep in mind. So because we are not talking about what are called the dual of that space, but we are talking about a new class of objects called bilinear forms. Okay, but this is enough. This information is good enough for our purpose. Therefore, now what we do, we are interested in constructing a basis for BR2. That's our objective. So we are investigating what exactly is the dimension of BR2. So for that we construct a basis. We make the following observation. Okay. So consider BR2. Let us work on this. Define four bilinear forms denoted by E2, because we know that what we do is we fix this on even EIEJ. If you do that, then you can extend it as bilinear forms on R2. I mean, that's the process that you do. So we fix what this by setting now you see that this is for I, comma j, comma L, comma k, that means if you just fix E1 say, if you just fix E1 say, then E1 on E1 comma E1 tensor product E1 on E1, for example, you see this E1 this is equal to 1. And E1 this is equal to 0. Therefore, this is not 0 bilinear form. What do you mean by a 0 bilinear form? Is the one that maps every ordered pair E1, E2 or x1, x2 or xy to 0. So this is not a 0. And of course then you extend this, because you know how it is extended. I already shown that once it is fixed on E1 E1, E1 E2, E1 E2 E1 and E2 E2, the corresponding bilinear form is completely determined. Okay. Therefore, the bilinear form E1 E1, E1 tensor product E1 is defined. So also E1 tensor product E2, E2 tensor product E1, E2 tensor product E3. So 4 bilinear forms are now well defined. Okay. Right. Now what do? We claim that these bilinear forms form a linearly independent set. So we claim okay. So all that you need to check is this, that is sigma Cij there are 4 terms of this equal to 0 for every I, j. That's what we want to prove, and that's quite easy to prove because you observe that just a very simple observation that sigma Cij Ei cross Ej acting over Ei comma Ej is equal to Cij. So that's a simple thing. All that you need is delta Jk, which implies belonging to So that is done. So they form a linearly independent set. Now what we assert is that this is a basis for how does it happen? So we prove that B is equal to sigma Bij, that is some number, Ei cross So let us work on this. So let us evaluate B xy. This is equal to sigma x1 e1 plus x2 e2 is the unique representation of x. So also y1 e1 plus y2 e2 represents uniquely y. That means these scalars x1, x2, etc., y1, y2 are determined. So Bij x1, x2 this is uniquely determined. Now if you evaluate this, what will you get? Okay, this is equal to see, use these properties and then evaluate it. Use the bilinearity of this form. Okay, then you get what is it? Yeah. So let us observe that Bij is equal to B of Eij. B of now this is easily verified. Okay, what does it mean? It means that B is, and you can show that Bxy is equal to this one. So using this you can show that Bxy equal to sigma B acting over R. This is not easy to, this is not difficult to do. It's just routine verification that you do. Okay. Because we expand on this side and expand on this side, here also you write b of xy in this form and then write down what the coefficients are, etc. Right? You will get the corresponding result, and this is very easily verified. Therefore, you see that this is a basis for, or these four vectors form a basis for, or these four bilinear forms form a basis for BR. That's going to be our main plank. Four-dimensional R with a basis given by E2. So that is the vector space structure of B1 of BR. Thus we can write thus B now this is the structure of any B, because you know that once B is given, these numbers are fixed, and this gives the representation for B, and that is the unique representation for B. Unique. Okay, so this is a very handy result for our further procedure. Now we look at the following. I mean, the motivation is this. Now you see that if we represent determinant of suppose we write this as where A1 equal to A11, A21, then you know that we have already seen that delta is a bilinear form. Delta is a bilinear form. This is easily verified. You also have this property that delta of, say in general, x, y equal to minus delta of yx. And one can easily verify that this is true. Further, you can also verify that or as a consequence of this. Now, this is a special class of bilinear form. Therefore, this is not a general bilinear form, but it's a special class of bilinear form. Okay. Further, you can prove the following, that is, this is equal to b of or delta of equal to 0. That's easily verified. And of course, delta of it's easily verified. So these are two important properties that this has, and of course this can be deducted from this property, because if you have delta of xx is equal to minus delta of xx, and therefore twice delta of xx equal to 0. Therefore delta of xx equal to 0. This is a consequence of the property. Now such or we can give the definition. B belonging to is said to be alternating if it's an alternating bilinear form. So determinant So naturally you ask, what is the general structure of a alternating bilinear? So let us do that, investigate that. Suppose B is alternating. Then of course we have B is equal to that is the general structure of a bilinear form. Now we are using the idea that B is alternating. Okay, right? B is alternating means B of E1, E2 equal to B of by X. So we make use of this. Therefore, suppose B is alternating. Now you see that a consequence of this, as I said earlier, is that if B is alternating, then B of EI is equal to 0. That is one of the observations that we make. Okay. Now B is alternating zero. Let us prove this. So you see that B of is also equal to minus B of B of twice equal to 0. This is true for every x belonging to R. What is the implication? So let us use that. Okay, so we will make use of this now. Therefore, we have which in particular if B is alternating, equal to 0 and B therefore you see that thus if B is alternating, B is equal to, let us work on this. B E1 E1 is 0, B E2 E2 is 0, therefore this is equal to B E1 E2 which implies which is equal to B E1 E2 into that is the structure. Okay, that is because B E1 E2 is equal to that's the reason. Therefore, B is in fact a scalar multiple of, thus B is a scalar multiple of E1 tensor product E2 minus E2 tensor product E1. That is B equal to E1. So that's what you have there. Okay. Now let us look at this class. Then it is easily verified that is a subspace of BR, and by the previous observation it is one dimensional with a basis So that forms a basis for this. Because there is only one non-zero vector, and every alternating bilinear form can be written as a scalar multiple of this. So that is done. Okay. Now, what more we have? So we have done the groundwork, basically the groundwork for this. Now we prove the main result, namely how the determinant, obviously determinant is a alternating bilinear form, therefore it is a scalar multiple of this. Okay. Now we make an observation, the following. What we want to prove is that if A is an alternating bilinear form, then okay, so let me pause this. Okay, now what we prove is this. So we start with the following, that is, we start with a 2 by 2 matrix. Let LR2 is a linear transformation on R2 represented by A2. Okay. Now we observe that if B is an alternating bilinear form, then B of okay, let us prove this. So let then we have B tilde xy equal to B of ay which is equal to minus b of ay ax, which by definition is b tilde minus b tilde x. This is true for every therefore b tilde is alternating. Okay, if b is alternating, then b tilde is alternating. So from what we have seen, b tilde can be written as a scalar multiple of the basis vector. So that's the computation that we are going to make. Therefore, some constant times because this is a basis, okay, where k is a constant. Now let us see how b tilde and b are related. Okay. So what we want to compute is the following. Okay. Now we want to show that actually b tilde is equal to determinant of A times B. So here that's the main result that we want to do. That is the scalar multiple that from which or which fixes b tilde is essentially the determinant of a transformation. So it comes out in a very natural way. Okay. So let us prove this. So b tilde is equal to, so all that we want to prove is this: b tilde xy equal to this is what we claim. It's enough to prove this for every so b tilde is equal to u. That's clear. What about b? B is also equal to c times u. Okay, we evaluate b tilde on E1, 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 E2, E1, 3 and so on. So, if B and B tilde agree on these vectors, then this is what you have. So, you observe that B tilde of B of E2 equal to so it is the values of B on E1 cross E2 and E2 cross E1 that fixes it. So let us compute that. Okay, B tilde of equal to K of and that's equal to simply K. Similarly, you have B of C. Therefore, you have the following. Oh, okay. So what we want is this, right? So let us compute the following. So we will compute this, that is B this is equal to B of, by definition, B of A E2. This is equal to B of, what is AE1? AE1 is a, say, see, A is equal to therefore AE1 similarly AE2 this we know. Therefore, B tilde of this is equal to B of A21 A12 E1 E2. Now expand this. You expand this, what do you get? You will get this is A11 A12 plus A11 A22 B plus A21 A12 B of E2 E1 plus A21 and because B E1 is 0, B E2 is 0, implies B tilde of E1 E2 equal to A11 A22 E1 E2. That's it. That's the computation. Okay. Therefore, you see that the following holds, namely it is B tilde okay. Now use this. If you use this, then you can easily see that. Therefore, from this you can easily see that B of this is a simple consequence of that for every xy. That's easily verified. Okay. Therefore, this is the result that we are seeing, where B tilde is or in other words, this is what you have, that is B of AX determinant of B of This is exactly what we wanted to prove. Okay, so the determinant of A comes up in a very natural way here. Okay, so the determinant of A is nothing but the scalar multiple involved when you write the alternating form B Ax Ay as a multiple of Bxy. This is the relationship. Okay, so this is the major result that you have. Therefore, determinant of A or the scaling factor So that's what determinant is all about in the case of a 2 by 2 matrix. Okay, which in a way shows that this is not a freak thing. There is definitely some structure that goes into it, into the making of the determinant. It comes out. So it's a sort of intrinsic number associated with A. That's the important part. Therefore, this is an intrinsic scalar that is associated with intrinsic. So this is all about the determinant in the case of a 2 by 2 matrix. Obviously, the question that you ask is this: is this statement true? The square matrix. So what we have defined as the determinant of an n by n matrix is this again having the same form. Now that will be our theme for investigation for future. Okay, thank you very much.